Garage doors come in many styles, colors, and materials. They can be made of steel, aluminum, wood, or vinyl. Whether you choose a style that's plain, paneled, smooth, or textured, quality garage doors are lightweight, well insulated, and airtight. The typical residential garage door is made up of 4 panels. Each one begins as a sheet of either aluminum or steel, 2 metals that can tolerate harsh climates. The side that will show has a baked-on coat of polyester paint. Depending on the model, the sheet passes through rollers that imprint a texture, such as a simulated wood grain. Then it goes through a press that imprints a design. This model will have raised rectangles. Others have horizontal stripes, or no design at all. After an automated machine cuts the continuous sheet to garage door widths, another machine folds over the edges. This creates half-inch joints for attaching the panels. The polyester paint is elastic, so it simply stretches with the bending. Now, on the back side of the sheets, they hot glue metal plates to reinforce the various components they'll later screw into the garage door. Parts such as the lift handles, the hinge, and the bracket for the electric opener mechanism. They also drill a hole through which they'll later inject insulation. Now they slide 2 sheets together to form a panel. They close off the ends with blocks of pine. This will prevent cold air from penetrating inside. They apply various stickers with installation, maintenance, and safety information. Orange stick-on dots mark the location of the metal plates into which the installer will screw the hinges and lift handles. They attach an aluminum bar to the long ends of each panel. This holds the panel steady during the injection process. After injection, the bars come off. They load the panels onto a carousel and begin the process of filling the hollow interior cavity with insulation. Through the hole they drilled earlier, they inject polyurethane foam, an expanding plastic insulation material that's specially designed to penetrate hard-to-access spaces. As we see in this demonstration, the polyurethane expands and becomes rigid. This creates a solid core inside the garage door. Polyurethane is one of the lightest types of insulation, so it doesn't make the garage door heavy. Here's what the inside of a panel looks like once the foam hardens. Now, workers install various components, such as the rubber weather seal on the bottom panel. This seal prevents cold air and water from entering the garage under the door. Some garage door models have windows to allow in natural light. Workers first use a high-speed router to remove the rectangles where these windows will be installed. Then they insert one of several window styles available. These are double-sealed windows, 2 thermal panes with an aluminum spacer in between. The framing around the glass comes in different colors. It's made of PVC, a synthetic resin that doesn't discolor. The frame prevents water and cold air from penetrating through the window. Workers pack the installation hardware. Then they weigh the box to ensure no part was left out. At installation time, they attach the door panels at the joints with hinges. A system of springs ensures the garage door is perfectly balanced and moves smoothly. If properly installed, you should be able to lift or lower the garage door using 2 fingers. Whether they're colored or clear, glass bottles and jars are green. No trees die to make this eco-friendly packaging. Glass is made of natural ingredients that are abundant. You can recycle glass endlessly, and making it uses less energy than producing metal or plastic. The recipe for glass combines about a half a dozen natural raw materials, but the main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It comprises about 15%. A limestone content of about 10% makes the finished glass more durable. They combine these ingredients with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. Over a full day, the fiery heat, 2,730 degrees Fahrenheit, melts everything together, producing a gooey liquid that's the consistency of honey. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical gobs. Each gob is the exact amount required to make one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar forming and bottle forming machines. A gob of molten glass goes into a preliminary mold. In a matter of seconds, it comes out as what's called a parison, a miniature version of the final bottle. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows the compressed air into the parison, stretching the glass outward toward the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-colored beer bottles. The color is produced by adding small amounts of iron, sulfur, and carbon to the glass mix. The factory uses a similar manufacturing process to produce other types of bottles and jars. In this run, the company is making 375 milliliter wine bottles out of clear glass. This run is producing 375 milliliter liquor bottles also out of clear glass. But this mold has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing leer. The bottles cool at a controlled rate as they move through the leer. This releases stress from the glass gradually. As the bottles exit the annealing leer, a sprayer coats their exteriors with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now line up in single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, a worker does a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that's an incentive to recycle. Goalie masks are all about putting up a tough front. It's not just their protective shell and cage. Their wild paint jobs are designed to intimidate. Incredibly, back in the 1960s, the first masked goalies were ridiculed by fans who viewed the mask as a sign of weakness. It was a case of adding insult to injury. Today, these masks allow the goaltender to play it safe, so they're far less likely to be sidelined by a serious injury. They start with a plaster mold of an average Joe. They plug the mouth hole with plasticine. This ensures that the mold won't spring any leaks while they fill it with plaster of Paris. They let it dry for half an hour. Then they pull off the initial mold to reveal the solid impression. They press plasticine onto strategic areas. This mimics the foam safety guards that cushion every mask. The final result is called a plug, and it will be used to make a two-part compression mold. After applying a black sealer, they polish it smooth, eliminating imperfections that would be visible on the mold they're going to make from it. Over at another station, a worker in protective garb unrolls fiberglass fabric. He cuts and layers sheets of it, then draws patterns onto the top one, spacing the shapes closely together to minimize waste. The goal is to score 100 goalie masks from one roll of material. Using a disc cutter, he slices through 25 layers of the fiberglass fabric. Then he stacks various composite fabrics, several of the fiberglass one and patches of Kevlar for reinforcement. Kevlar can absorb so much impact, it's also used to make bulletproof vests. He places more fabric over the Kevlar. He spreads an epoxy resin onto each layer. He drapes them over a mold that's been made from the plug and smooths the material to eliminate air pockets as he continues to layer and glue. He's laminating all the pieces together to form one. He trims away the ragged edges and then places the inside portion of the mold into the outside one. The wet fabric is now sandwiched between two mold pieces. He lowers a 1-ton press to compress the layers of fabric as the resins between them continue to form a bond. He adds some clamps to keep things tight. After 20 minutes, he pries the laminated fiberglass shell out of the mold. This is one very tough shell. It's the raw form of a goalie mask, but it still needs a lot of work. So it's over to the trimming and grinding station. He places a trim jig over the shell. Using a high-speed router, he cuts an opening for the cage. He slices off the flash with a disc grinder. And then he sands and grinds the edges. He drills holes to attach various fasteners. Then he carves out larger holes for ventilation and to reduce the mask's weight. Coming up next, watch as the paint pros go to work on these shells. They prep the mask by roughing it up with an orbital sander. Then they pour a sealer into a container. The technician wears a charcoal respirator because the emissions are toxic. He adds the activator solution and a reactive reducer and stirs the sealer together. Then he sprays the sealer mix onto the masks. The finish will cure and harden as the chemicals in it generate their own heat. Next, this system stirs up some Hot Hues automotive paint as the technician sprays a vivid gold base coat onto the masks. Computer graphics created with SignLab software are sent to a plotter that cuts out adhesive vinyl paint masks. He pulls away unneeded vinyl around the stencil, a process called weeding. Then he presses the vinyl stencils against the Goalie mask and peels off the paper backing. Applying a stencil to the crown is tricky because the surface is curved with ridges, so it doesn't lay flat. He lifts and cuts the pattern with a utility knife and then straightens it out. This mask is starting to look pretty impressive. But they cover the whole thing with white paint. It's a temporary cover-up. This process is all about layering patterns and color. They apply more vinyl shapes, and then, using a pressurized paint system, they spray everything bright red. Next, an artist airbrushes some shadowing onto the now barely visible image of a leaf. He peels away some of the paint mask vinyl. And it's time for a really neat effect. He sprinkles the surface of the mask with water. Then he mists it with paint, and the water droplets catch the paint. He blasts it with a heat gun. The water evaporates, but the paint dries in droplet form, giving the mask a frosty look. He airbrushes a drop shadow around some lettering, dispensing with the usual safety gloves for this detail work. And now all is revealed as he peels away the vinyl. The Goalie mask is showing its true colors. But wait, a little touch-up job is needed. He traces the pattern onto see-through paper and then transfers it onto Bristol board. He cuts it out with a utility knife. Then he aligns it with a shape on the mask and precisely airbrushes around it to make the smudge disappear. With the final clear coat, this mask has visual impact. It makes a colorful statement. And now it's time to put all the pieces together. She screws on the stainless steel cage and applies a little glue to reinforce the adhesive-backed foam cushioning. She attaches the sweatband with Velcro so it can be removed and washed. And then she moves on to the backplate. She threads the harness through the backplate to the front of the mask to attach them. The harness is elastic, so it gives the mask some flexibility. Now it's ready for some ice time. And with their various custom paint jobs, these masks all say the puck stops here. Gold jewelry has been a symbol of wealth and status throughout the ages. Today, though, it isn't just for the rich. Even ordinary people are likely to have a gold ring or necklace, just a little less diamond-studded. As early as 2000 BC, Egyptian kings and queens adorned themselves in golden jewelry encrusted with precious gems. When the Spanish sailed to the New World in 1492, they discovered Mayan and Aztec masterpieces of colored stones and pure gold. Today, elaborate gold jewelry and precious gems are well beyond the reach of the average person, except for the diamond ring, still the customary symbol of engagements. The client and the jewelry designer first decide how the ring will look. The designer then measures the client's finger to determine her ring size. He then sketches out the design they've agreed upon, a grooved band with 3 diamonds. The model maker works with a special carving wax. Using a compass, he measures and marks the width of the band, then carefully saws it off. He takes his gauge and puts it on a stick with ring size markings, called a mandrel. He adjusts his compass to the ring size, then scores the finger hole on the block of wax. He then takes his drill and carefully carves out the hole he scored. Then he grinds off the wax on the outside of the band. Using the compass again, he scores the middle of the band where he'll make the groove. Then, using a fine drill bit, he carves out the groove. With a file, he then refines the groove and shapes the curves of the ring according to the design. After putting wax prongs on the band, he attaches a wax stem to the model. He then positions the stem into the base of the cylinder that the jeweler will use to cast the ring. The base goes onto the platform of a vacuum machine. The jeweler puts a cylinder on top of the base, then pours in a special plaster. The vacuum sucks all the air out of the plaster. This is a key part of the process, because if any air bubbles remain, the finished ring will be out of shape. In less than a minute, the vacuuming is done, and the cylinder goes into the furnace at 1350 degrees Fahrenheit. The wax model evaporates, leaving a void the exact shape of the ring in the hardened plaster. Next, they melt the gold. The gold content of jewelry is measured by carat. The lower the carat, the less gold and the more alloy, or cheaper metals such as nickel, silver, and copper. After 5 hours, the cylinder comes out of the furnace and goes into the casting machine. The machine spins for about a minute. The centrifugal force shoots the liquefied gold into the plaster mold that's inside the cylinder. The jeweler then immerses the cylinder in cold water. This cools the gold and makes the plaster disintegrate. What's left is the cast gold ring, but its surface is rough, so on to the finishing process. The jeweler saws off the stem and gets to work. He files and grinds the ring until the surface is smooth. Then he stamps on his trademark and the carat marking. Then he hammers the ring on the mandrel to make it perfectly round. The jeweler then hands it off to a specialist in polishing. The polisher runs the ring against a series of buffing wheels until it's bright and shiny. The polisher then hands it off to a specialist in setting gemstones. The setter straightens the prongs that'll hold the diamonds. Then, with a delicate drill bit, he carefully carves out the inside of the prongs. The edges of the diamonds will fit directly into these slots. He readjusts the prongs, then sets the diamonds, making sure the prongs hold them down securely. That's a 1-carat diamond in the middle, a 1/2-carat diamond on each side. The jeweler then immerses the finished ring into the ultrasonic machine. The vibrations in the water penetrate every nook and cranny, washing the ring. Finally, he puts the ring under a jet of hot steam to blast away any remaining residue. And voila! With a ring like that, who wouldn't say, I do? Fishing may not be rocket science, but the graphite fly rod certainly is. Graphite is a space-age material, lightweight, flexible, and strong. The very qualities that make it useful in space also come in handy at the river or lake. It explains why graphite fly rods are now popular in the fishing world. To make one, they start with a sheet of graphite. They cut out shapes following precise measurements. One mistake here and the performance of the rod will be compromised. This will be a 3-piece rod with a butt piece, midsection, and tip. They place a shape on a tapered steel mandrel and peel away the paper backing. This machine rolls the graphite shape around the mandrel. They make all 3 sections of the fishing rod the same way. A graphite strip at the end reinforces it all. The graphite remains on the mandrel for the next step. They wind polypropylene tape around the graphite to squeeze out any air pockets between the layers. Then it's into the oven to cook at 257 degrees Fahrenheit for an hour and a half. The tape won't melt, but resins in the graphite will, baking the rolled layers together. Afterwards, they remove the shrink tape and pull the graphite blank off the steel mandrel. Then the rod blanks go for a dip in a special finish, which turns it a deep blue. They bake on the finish for a half hour at 257 degrees Fahrenheit. Afterwards, they measure the rod sections and cut them to size, so they all fit together. Bending without snapping is the graphite rod's strong point. They hot glue the stainless steel tip to the end. Then they piece together the retainer for the fishing reel. This lock nut will allow the reel to be tightened. The plug will keep everything from sliding off. They glue cork rings together to make a handle. Then they shape it with a chisel and sandpaper. The line guides go on next. They keep things from getting into a tangle. They wind thread around it to secure it to the rod, 1 foot at a time. A final step ensures the handiwork doesn't unravel. They place the rod in a rotating jig and brush 3 coats of glossy epoxy onto the thread wrap. This not only protects it, but gives it a nice finish. Now they slide a metal foot into a groove on the reel retainer, and it's ready for the reel to be attached. But before you can cast your line, there is some information that needs to go on the rod, like the brand name and serial number. A final inspection, and it's almost time to test the waters. The reel snaps into place, and it's easily adjusted with a lock nut. The rest is a matter of luck and the right bait. Despite the name lead, the core of a pencil isn't actually made of lead. It's made primarily of graphite, a form of carbon that's very abundant in the Earth's crust. To produce pencil leads, they combine graphite powder with water and clay. The higher the ratio of clay, the harder the lead. Quality graphite pencil leads don't break easily and glide smoothly on the page. Graphite is mined from both open pit mines and shaft mines, like this one in Germany. Miners use hammer drills to bore holes for explosives. The chunks of ore must contain at least 30% graphite to make the area financially viable for mining. At the surface, a crusher breaks the ore into small pieces. Then, adding water and oil, they pulverize it in a rotating mill. This ore soup then flows into a system that separates the graphite from the impurities. The graphite particles cling to the air bubbles and float to the surface. Skimmers send this layer of graphite foam back into the mill. 5 cycles later, the graphite concentration is 96%. However, it's soaking wet, so it has to go into a dryer. After spinning around at 572 degrees Fahrenheit for about 30 seconds, the graphite becomes a completely dry, fine powder. Mined and processed, it's ready to be shipped to the pencil factory. To make pencil leads, the factory combines graphite powder with clay and water. During the 35-minute mixing cycle, it's critical to control the blending speed, pressure, temperature, and moisture level. This produces homogeneous granules, the key to ensuring that all the leads will be uniform in quality. The granules go into a hydraulic press, which shapes them into a cylindrical block. Workers then wrap the block in film to prevent drying out and set it aside for a week to cure. They load each cured block into a hydraulic press, which pushes it through a forming die, producing one long continuous lead. Different dies give different sized leads. The next machine then cuts the continuous lead into pencil lengths. The leads are the right thickness and length, but they're soft and pliable because they still contain water from the mixing process. Workers load the leads into a rotary dryer at 320 degrees Fahrenheit. 12 hours later, the leads exit the dryer straight, but not quite strong enough. So next, they go into a kiln for 10 hours at more than 1800 degrees Fahrenheit. This firing transforms the clay that's mixed with the graphite, strengthening the leads to their final hardness. Finally, a 12-hour bath in a mixture of high-quality waxes. The waxes fill the pores in the leads, leaving them with a surface that glides smoothly across paper. Throughout the production process, the factory puts samples through quality control testing to check hardness, break resistance, diameter, and of course, writing quality. This company produces 3 different qualities of graphite leads in 16 different hardness levels, plus a full array of colored leads, made similarly, but with pigment powders and waxes rather than graphite.